Hello everyone, welcome to my channel. This is the first part of lecture of fluid mechanics. So to study the behavior of fluid, uh, we use the Navier Stockes equation, which is a combination of the continuity equation and the conservation of momentum. In this video, I will discussing the continuity equation. The learning objective is to derive the equation and to understand their terms. So the continuity equation states that the rho dt plus divergence of rho v equal to 0, where rho is the density of fluid and v is the velocity vector. Now let's talk about continuity equation in general. We note L, the intensive property. L is something that is independent of the amount of material you have. For example, the temperature, the density rho of, or the density rho of fluid. We note also omega as the control volume of fluid, the omega as the bounding surface area. Now using the Reynolds transport theorem, which states that time derivative of the integral over the volume of L dv is equal to minus the integral of over the surface, the omega v is dot n, where n is the normal vector, minus the integral over the volume of q. Now we will try to describe each term. So the first term is the rate of change in the property L. Second term is how much of property L is leaving the volume by flowing over the boundary the omega. And the last term is a sink term, how much of property L is leaving due to sink or source inside the boundary. Now to understand the difference for Q positive we have a source flow, and for Q negative we have a sink flow. Now using the divergence theorem, which states that every integral over the surface can be written as integral over the volume by using the divergence formula. Now we use this theorem in our case, and we find that we have all the integral over the volume. Now using the Leibniz rules, which help us to make the permutation between the derivative and the integral, we use this rule in our case. So we enter the time derivative in the integral over the volume, and we have in result all the terms that are integrated over the volume. Now this equation applies to any control volume. So the only way the above equality remains true for all controlled volume is if the integrand itself is 0. Thus we arrive at the general form of the continuity equation. Now we apply the continuity equation to density, because density is an intensive property. It is equivalent to the mass, and we have in the end this result and this equation. This equation operates with a constant control volume with no source or sink of mass, so Q will be equal to 0. In some cases, such as when we have pipe pumping fluid in or out the system inside the control volume, we might not want to assume Q equal to 0. However, for general cases, we make assumption that mass is not added or removed from the system. However, in certain cases, it is useful to simplify it further. For example, for incompressible fluid, the density is constant. We obtain the simplest form of the equation. Divergence of the velocity is equal to 0. So now we arrive at the end of this video. We will talk in the next video about the conservation of momentum. So thanks for watching.